Apologies for the delay. Unfortunately, no unavoidable circumstances, I could not come on time. But I'll be taking the class, and you can look at the recording as well. And of course, you can look at the recording. Right. So, yeah, apologies for this late start. We can get started in 10 minutes. Am I audible? Hello? Come on. Okay, so good evening, everyone. So this is the last live interactive session, and once again, I apologize for the delay. Um, so many disturbances today, so unavoidable circumstances which had a personal emergency, so could not make it on time. But I'll make it up for it on the recording, and you can take a look at the recording. If you have any questions, you can message me, mail me, or even chat, ping me on the same chat from the same meeting, right? And since today it is the last, it is the last installment of weekly live sessions. So I was thinking we'll run through everything that we've learned so far in ACN. I mean, if not everything, just the topics at least, right? So what did we learn in that topic, and what what is expected that you have understood about networks uh, from going through all of this, and then come to today's topic, which is named data networks. But I do not plan on spending a lot of time on named data networking. Instead of that, I was thinking I will share with you practical tutorial on how to perform P4 programs, right? So how to run P4 programs is data plane programming. That's exactly an interesting concept, and I did introduce that in the previous class. In the data plane programming class, I did do this, but I think this would be a slightly deeper dive into the P4 programming aspect of what we're doing, into the data plane programming aspect of this course, to give you a practical flavor of what you can expect, right? If you want to work on next generation networks, right? So as usual, we go through the questions for this week, and we build on from there. And when I say build on, I'm going to start from the very first topic and just read through the topics so that you can. So it'll serve like a recap, I believe, because I think your exams are also down, correct? Those if you're taking your exams. Yeah, let's take a look. So how many packets are used in the named data networking architecture? So this is nothing but another architecture. Last time we saw something called information-centric networking, right? So this is the advanced version of information-centric networking, I think. Or another, it's another uh, similar architecture, right? Where we use concept of names to identify resources or objects on the internet. So here the question is, how many packets are used in Indian architecture to retrieve a named chunk from a content provider? The one, two, three, or four. The direct question from the theory. What video you can understand this. Right? How does Indian handle data cache? So how in the Indian architecture, how is data caching handled? Right? That is one. It's also once again directly connected to the named data networking. And which of the following statements are correct about named data networking and IP architectures? Okay, so it's a comparison between IP and NDN. So it says NDN network, like IP packet delivery, employs best effort data retrieval. NDN architecture has a stateless data plane, whereas IP has a stateful data plane. Let's see. So IP includes security perimeter directly at the networking layer. Okay. So one interest packet can fetch multiple data packets in named data network. Um, Again, this follows from the way they've defined named data networking. All these answers are directly from uh, going through the video for this week. And then the routing plane of IP is dumb. The routing plane of IP is dumb, whereas the routing plane of NDN is smart. Let's see. And which of the following problems were addressed by NDN name-based routing? Will address field exhaustion? Is it the map traversal problem? Is the network address translation problem? Not exactly a problem, uh, but okay. So guarantees no data loss because in current architecture you have data loss. And then is it because of address management? Which of the problem is, is or are addressed? It should be multiple as well. The following is a key difference between the CSN fit tables in NDN. So this is directly from the way NDN is defined. CS is used to forward interest to the next hop, while fit is used to store data. CS is used to store the interest of the unresponsive data, while the PIT is used to store data. And this is basically the converse of the previous one. And then CS is used to store data, while the fit is used to store interest of the unresponsive data. CS is used to store incoming interfaces, while the PIT is used to forward interest to the next. Okay. And again, whole lecture is about NDN. So which of the following are the reasons why NDN may be more efficient than IP in terms of network resource usage? Um, Data packets can be cached at intermediate nodes. Interest that data packets can be forwarded to multiple producers or consumers. Interest packets are always routed towards the content producer. The shortest path. Indian networking paradigm do not pose data privacy or availability. Um, okay, let's take a look. The following statements are correct about the naming in NDN. So how is naming done? Because of the hierarchical naming convention, or the names are generated by the application, or depending on the type of application, or the user's application developers not have the ability to define their own naming convention. Okay. And NDN does not support flat naming models. So previously in centric networking, we had three naming conventions, right? One was flat, the other one was hierarchical, and was hierarchical. The third is flat, hierarchical, and then flat, hierarchical, and attribute based. Right. So in the flat, I'm talking about information centric networking. Okay. I'm talking about information centric networking, where there were three hierarchies, meaning three different types of naming nomenclature, where flat would just mean that you hash the name of the object and you append that hash to the name, right, to make it unique. And hierarchical is where you have a nomenclature in terms of slashes, like this folder one, or in the same way you have your file system, folder one, folder two, slash something, something, slash something, and then you get the name of the object. Someone else having the same name will have a different hierarchy. Right? So that is one way in which this is all the clash of same names. And the next is attribute based, where we some files like um, songs or videos, and they have a runtime, correct? Some time it runs the encoding of it, like is it MP4 or is it thing is what is the bit rate of it? Right? So all of these are attributes. And they're all attributes of the particular file. So you append this attribute to the file name and you're done. You get a unique file name. So let's take a look at this. So in a standard NDN architecture, how many data structures does each router typically maintain in order to process NDN packets? Okay, okay. This is again a direct answer. Um, and which of the following statements are correct about the security aspects of NDN, right? Content producer will cryptographically sign the data packet. Um, System cannot be attacked using information obtained from the identifier. NDN uses end-to-end encryption to protect content in transit, and encryption is mandatory for the data packets transmitted over the network. What is the role of the Indian trust model? To ensure data availability, to ensure the packet is delivered to the requesters, to ensure data authenticity and integrity, to manage network resources. Right, so with this, I'll switch over the screen, then we can start writing. Right, I was muted. Okay. Sorry about that. Oh, so let's try the last class. One I was thinking maybe we could just have a brief look on what all happened so far in ACN, and just to jot your memory on the thing that you have learned so far, right? It will probably serve as a reminder before you go into your exams, if at all you do. So of course, we'll do that first, and then we'll quickly answer these questions. But these are all very direct questions from the video. So watch the video, you can find the answers to this. We'll provide the answers for these questions. And then with the remaining time, let's have a practical hands-on for P4 programming. Right? Okay, now moving on to the first one. Here, you see, right? Let's have a look. For your week one, right? Your first week. You you got introduced to the world of routers, switches, right? So probably if you had studied networks before, um, you might not have paid much attention to these devices, but now in advanced computer networks, you were looking at how these network devices work, correct? Work. So what are all these steps involved? Because when I myself did study network, basic program networks, I didn't pay much attention to these aspects. But then this is a whole, it's a huge ocean. So there are specific algorithms. Specific algorithms that are employed for network devices. And this is what you discovered, right? And the part of this is also that you also understood that routers, they have tables, correct? Routers or switches. And you do something called a lookup on a table, correct? You do a lookup on a table. And you look up on a table which contains some entries. And so this was a new paradigm or a new aspect altogether. So this is what you studied in week one of HCN. Week two, and yeah, by the way, this is about these devices work, and these are all high performance switching and routing. This is what is called high performance switching and routing, right? Okay. So week two introduced you to an aspect of these network devices, or rather, the algorithms that are used. The algorithms, or it can also be data structures. Okay, are used by the networking world. Okay. So what makes this special? It's because these algorithms are designed to work to reduce the complexity, right? So to reduce the complexity of either packet lookups or address lookups or either of these operations, right? So address lookups, etc. As part of this, you looked at the data structure called try. Right? So you mainly looked at the basic tries and you looked at some optimized versions of it. These try. And essentially, you got so the takeaway from this was basically how your addresses or table entries, okay, how your table entry are represented in memory in order to entertain high speed operations. Um, Now, moving on from week two to week three, you looked at packet classification and traffic management, or you can also call it traffic shaping. Okay. Um, so this packet classification, this is also a set of algorithms, right, which can applied on a packet through the switch extensions or switch uh, tables, let's say. You can classify this packet in the sense that, okay, I want to allow this packet or I want to deny this packet. Let's say, for example, a firewall. So how do you match the header fields of a packet with the entries in the table in such a way that you can determine or you can take some actions based on that? So this was week 3, and probably if you want to learn more about these topics, there's a book called Network Algorithmic. By George Verwey. All right, so far you were slightly in the familiar domain only, right? And then week 4 continued on the same topic, continued on traffic management. Right? And then I discussed a little bit about the switching fabric as well. So this fabric is not cloth. So basically, this is the way a switch is able to take a packet coming from one port and then put it exactly on the port to which it's destined. So this hardware design, this fabric is called switching fabric. So how was it designed, right? And we saw multiple variants there. And of course, I think I missed out talking about the memory. So the memory was basically SRAM and DCAM, right? So these are the two different types of memories, and the SRAM memory is able to uh, allow matches, is able to allow exact matches, but TCAM can allow exact as well as ternary. So what that means is you have a packet that's coming, header field, right? It's a header field, and this packet, and there is a table over here in SRAM, let's say. So this is matched exactly to the table entries, and only if there's an exact match, it will take some action. But if you want to allow, you want to allow everything, right? Let's say I don't care what the header field is. I only care what the other header field is. Then you can just put a star value, which is called ternary operator, which means you doesn't matter if there are two header fields, so h2, 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 and this is some values for this h2. So this packet will match with one of these, and you completely ignore the first header. Essentially, I think we've explained in the video as well that I took. So these are the two different types of memories that these switching fabric or other these network devices leverage. Right? And then we spoke about the history of internet in week 5. About something called the internet and past. And why there was network softwareization. And what was network classification. I'll explain this thing very briefly and why this led to network virtualization. Why this led to network virtualization. Right? Then we saw network function virtualization. So I'll just give you a brief reminder or so that I can remember what you learned. So the internet, as we knew, started in It started in I think 1970s to our planet, 60s or 70s. To the point where right now we are completely dependent on the internet. Right? But as internet grew, what I mean by that is internet was nothing but a set of protocols. You have a node here, you have a node here. This node has a knowledge of some protocol P1, P2. This node here has knowledge of protocol P1, P2, P3. Only if both the nodes have knowledge of the same protocols will they be able to communicate. Correct. So you need to have the same. So basically, you need to have the same set of protocols on both the ends, or rather, the knowledge of the protocols should be uniform across both the nodes. And these nodes are separate computers owned by someone else, is owned by someone else. And these protocols, more often than ever, they are hard coded. Network device. The problem that happened was if in case someone came up with protocol P4, right? Which P4 is another protocol. And it's not the P4 language that they will look at. It's just an example, generic example that I'm taking. So you had to basically either the replace the device, right? Basically, that's what you have to do. You have to replace the device. So this did not spur innovation. Things were happening very slow. Network evolved at a very slow pace, right? So we're talking about this with respect to the internet impact and the network ossification. This is basically ossification, right? So the network stack became ossified. The network stack is nothing but the protocols associated with all the layers, and innovation was difficult. So they came up with something called network function virtualization, NFV. This also, I think, must be familiar. Because NFV was nothing but you take these network functions. So what are these network functions? Functions are routing, or you can also call them firewalls. Firewall is also a network function. NAT, network address translation. These are all specific functions in the network. And most of these functions happened at the data plane. When I say data plane, it happened on the device. But now what the paradigm that came up was offload every one of these to the software, right? So you get the input as packets, and then you take a decision in the software, and you send it away, right? So there is a software node that is sitting in between, that is sitting on the path of the packets, right? So if the packets are going from A to B, right? So there's a small bump in the wire, you can say, and the decision maker is sitting over here. And is that decision maker is can be called as NFC, network function virtualization, right? So and now week 6, you got introduced to software defined network, SDN. So must have been a slightly confusing transition because you just studied network function virtualization, and then now you're looking at software defined networking. So generally, we don't understand these two is SDN. It basically creates proper abstractions between control plane and data plane, right? Network was divided into data plane and the control plane on the top. Right? So these are all routers, right? Their control planes are over here. Sorry, their control, what do you call the brain? The brain of these devices are centralized. They communicate. So previously, how was it? Previously, control plane and the data plane used to reside on the same device. Right? So now this gives a more centralized approach to networking. Why is this important? Why is SDN important? It's important, or rather, it was novel because it was novel because you can observe the traffic that is not just inbound to this particular device, but to here and here as well. You can observe the links between them. So you can take a global decision. You can take a global decision based on what you have observed based on the network conditions. Okay. So in the paradigm of I'm not going into great details, but you also saw something called open flow. So what was this open flow, or what is this open flow? Open flow is nothing but standard data plane. Right? So it's a standard by which to communicate with the switches in the data plane. Why was this brought up? This was brought up because they wanted to avoid fragmentation. It should not be like one set of vendors have a different communication protocol, and the other set of vendors have a different communication protocol. So there are switches which came up open flow support, which meant that the switch should understand open flow commands. So what did open flow have? It had a set of messages, how do you start communication, um, if we look at packet ins, packet outs, and all of those nuances about open flow. And that every switch which is open flow compatible will understand these messages. So you can write your own program in any language that you want. You can say C, for example, I'm saying, and then you can call the OpenFlow library, and you can use their functions to communicate with the switch to instruct the switch to do X, Y, Z. Right? And once again, I want you to remember every switch has tables, and the OpenFlow is basically communicating with the tables, adding entries, adding and deleting entries. If you look at the whole paradigm, the crux is basically just adding and deleting entries from the network devices. That's basically how networking has been working, and it still works that way only. You get packets, the packets are looked up on tables, and based on that, they're sent. How these tables are created depends upon multiple algorithms that you use. Either you do it in the control plane, or you do it in NFVs, or you do it in multiple other what do you call it? You can basically get own program as well. Now in week 7 was only about NFTs. So we look at what the function virtualization was, and what are the basic concepts of NFTs, and what is the main, or what do you see that is different between NFP and STN. So if you remember, STN is a way of extracting NFPs, um, can help build better infrastructure, and basically the aspect here is you are softwareizing the network. So every process that happens is put into software. But of course, what is the problem with NFP? It reduces your packet throughput. Whenever you do something on software, it reduces the throughput by doing it on a general purpose signal. If you do it on specialized hardware, like routers or switches, it will fast. The same thing on software, it's going to be weak. It's going to be slow, right? And then we went into week 8. And in week 8, we saw programmable data plane. And in programmable data planes, we saw something called P4. So what was the difference here? Programmable data planes. So essentially, you had the brains in the control plane, right? And the muscles in the data plane. So whatever the brain says, the muscles will do. Similarly, whatever the control plane says, or the controller says, the switches will do. These are all switches, by the way. I'm giving a different name just to. Either the controller and just basically the brains and the muscles. So what if you take a part of that brain and put it in the muscle? Put it in the muscle, right? So the muscles can themselves think also, and they can themselves take action also. This is the best analogy I think I would say for programmable data, right? PDPs to call it. And you have a part of the brain here. So how do you program this brain? Using a language called P4. Right? So we'll take a look. We have time today of an example P4 program. So week 8, and then week 9 was about data center networking. So now till week 8, you have seen the fabric, the switching fabric, and the advanced concepts of programmable data planes and what came before that, which is software defined networking. Now you're going into a specific domain called data center networking. DC. So what made data center networking different from normal networking? TCP in normal internet and TCP in data centers, right? These two things are having stark differences. What is the reason? Latency. What is the latency? Is that in a data center, all the devices are controlled by a single entity, correct? Controlled in the sense under the same administrative domain. Or same administrative domain, which means the connections are high-speed connections, and they are in a geographically smaller location. Right? They are in a geographically smaller location, which means the latencies are of the order of microseconds. Right? But if you connect data center to someone, let's say it's your home, then has many kilometers in between, and it will also have multiple other nodes in between. So there are switching delays, there are propagation delays, and there are transmission delays. You must have heard that in your basic networking course. And these things will add up and will probably be in millisecond to second delays. So the point is, TCP that works here will not work great for this scenario. And we saw many problems like incast problems, which led to the we saw a major problem called incast problem, which led to the conception of something called DCTCP. This data center TCP. So how did data center TCP solve the problem? I won't go deep. I'll just say uh, it controlled the congestion window based on the queue of the switchboard. The fullness, which is the fullness of the queue of this switchboard. Okay, so this was easy TCP, and you also saw different topologies of the network battery, or you can basically say you have a pod topology. It's arranged like this. So it is like lower levels, and then you have aggregations, and then you have further aggregations, and then you have bigger aggregation, right? So this is how data center networks are organized mostly. And then as part of week 10, so network telemetry, and we also saw the paradigm of serverless computing. As a part of this, I showed a demo, or rather a video that showed how I used serverless computing to do an IoT project and using Amazon. Basically, network telemetry is nothing but extra information. You keep it like this: extra about the flows of a network that can help take better actions or better decisions. An example: if I know that the flow delay between here and here is large, then I know that something is wrong with this link. Right? So that will help me take a decision that, okay, let me inspect it. That is basically what network telemetry is. And you have a minor framework for this. But essentially, network telemetry, you can offload it to P4 based data planes as well. You can write your own programs to calculate or gather this network telemetry. And in this demonstration, we saw how we just called functions. Right? We do not write any code. We just called some functions and we tuned it as per our need. And basically, you could save data on database. We saw this on Amazon AWS. Right? You could save data, you could retrieve data, and eventually, you're not writing your own code, you're not managing your own infrastructure also. You're just calling functions. So you have no idea about what is the underlying hardware being used. The only exposed part of the whole paradigm are these functions. So this is serverless. Does not mean there are no servers. It means you don't know how many servers you're using. You just know you're going to call a function and it will auto scale. It will handle the queries as and when it comes. Right. So this is serverless computing. And of course, we saw as, and then as, right? Okay. Virtual servers, fast, and then serverless, and then comes Infrastructure is you basically use the same. I mean, so infrastructure is like so infrastructure as a service is that you rent out hardware, and you install your OS by yourself, and then you write your own code, right? And platform as a service is hardware and the OS is given. Then you just write your own code. Right? So this is the AAS. And then finally, serverless, you don't write your own code also, you just call functions. And these functions can be tuned to your needs. And you have no idea which OS and how many servers they're using, right? Hardware. I'm just explaining in very simple terms. Right? And finally, SaaS, software as a service. This paradigm is where you install, I mean, you don't install, you don't do anything. You go to gmail.com. In a way, that is software as a service. You just go into it on your browser and you're using that software. You're not installing that software on your own system. It's there in the cloud. You don't know how many servers it uses or how many um, different OS it uses. Another example is Google Docs. If you want an Indian example, you have Zoho as well. So this was week 10. And then week 11, last week, you saw how quick does its job, which is basically UDP based reliable delivery scheme, right? And then we also looked at content distribution network, CDN, nothing more. And then distribution networks. And of course, you have over IP networks. IP is current networks where you have to headers, you route packets using IP addresses. So you're actually okay. I'll come to that.
Sir, you're not audible to us.
I think now we should be audible. Hello. Okay, I think yes, now it should be audible. Okay, now it should be audible. Right. So let's just quickly go through the questions. Second, oh, all right. You want to continue after CDMs. Right. Okay. So I was just recapping. Um, I was just recapping what we've already done in the previous lectures. So, okay. So, okay, I'll start a little bit before that also, in case. So we looked at in week 10, we looked at network telemetry, and then we looked at serverless computing as well, and showed you a small demonstration on. You can refer these videos if you want to. I showed you a small demonstration on how the serverless computing can be leveraged to develop an application at a very short span of time, right? So what was done there was it was an IoT application that could sense the heat, and based on the heat, it takes some actions. So we we did all of this in a very short span of time because we didn't have to take care of any infrastructure as it is. We didn't have to take care of the operating system, nor the infra, and nor any of those. Right? And then information as a service, sorry, infrastructure as a service, platform as a service, and then serverless, and then comes software. Keep this hierarchy in mind. And if you look at the corresponding video, you'll have taken a picture from your NPTEL videos, which is pretty much apt to explain this. So it's got some more information also. You can take a look. Right. So in week 11, you saw something called PIC. PIC was PIC is nothing but a protocol. So we have TCP, we have UDP. So what is TCP? TCP is a reliable communication protocol. UDP is unreliable. This much everybody would be knowing. But what happens when you have okay, so what happens? What is the difference? So basically, you have a piece of information saying hi. If you say send it using TCP, then you can be assured that the message will go to the other person. But if you send it using UDP, you might not be able to. So this is like sending it. UDP is like sending it through a friend whose suitcase is completely full, and he may or may not use it all the way. But TCP is like sending it through FedEx or Speed Post, that you can track it and then you can see that it has reached the intended destination. Right? So this happens through multiple mechanisms like attacks, timeouts, and everything. Right? So where is PIC coming in now? PIC is basically using UDP to simulate TCP. In a sense, I don't want to fall into the nuances of TCP because TCP has some disadvantages also. At the same time, I want to have my free hand and I'll manage everything that TCP does at the application level. So that was quick. So if you go to Google Chrome right now, and if you communicate with youtube.com or google.com, it's all quick. You can capture it using Wireshark and you can see. And regarding Wireshark, I've already shown you how to capture packets using Wireshark. And these are nothing to do with the exam. This is just me showing you the practical aspects of networking. That's all. So no one's going to ask you anything about Wireshark in your exams. So right. So you have PIC, and then you have a factor that's running on UDP. So because it is running on UDP, it does not see the usual shortcomings that a TCP connection basically has. Right. So there's something called, I don't want to complicate with this, but you keep it like this. UDP or QUIC uses a particular cheat code in networks. So if you just give you you can take a look. It's an interesting read. So when comparing with TCP flows, uh, once again. So when comparing with TCP flows, PIC is unfair to TCP by consuming more than twice its fair share of bottleneck bandwidth. So you can take a look at this don't have time to go to the details of this, but yeah, going below. So now continuing from CDN to the original question, right? I think so. Okay.
Again, you're not audible, sir.
I should be audible now. Yeah, I am audible now. Yeah, thanks. I wonder why this is happening. Okay, now right after content distribution networks, we went into something called information-centric networking, right? So I'll explain this again possibly. So information-centric networking is nothing but a concept. Because in current internet, you are having two nodes. Let's say this is server, and this is you, and there's your friend, and this is the internet. And then you are requesting some data from the server, and it goes like this. Then it's, how you're requesting the data, you are saying you're requesting, you're creating a packet, and then this packet you're putting, you go to the server address. Let's say server address 10.0.1.1. Just an example IP address. In fact, this is a private IP address, so this won't be the actual public IP address of the server, just for example. All right. And then you are requesting for cat.jpg. Okay. And your sorry, your friend is requesting for cat.jpg, and you are requesting for dog.jpg. It's nothing but an image file. So this packet happily goes along here. This packet happily goes along the same route, and this packet also goes along the route, and then you get the response back as dog.jpg, and then you get the response back here is cat.jpg, and then you're able to see the image. So what is the fundamental aspect of this communication, this IP communication? It is the IP address, right? So that is the pivotal thing among all of this. So the IP address is the main aspect of this, to routing, or to, in fact, IP address is the main aspect for the whole of the internet, right? So Now, information-centric networking wants to change all of that. So how? How does it want to change all of that? Information-centric networking says that you don't go to a particular destination to get this particular file. You want to get something. For example, if you want to get cat, you just say, I want cat. That's all. Or I want dog. So what happens here is instead of the address being the pivotal aspect, the name of that particular resource, correct? Or the particular information. The name of the information becomes important. So under this paradigm, what happens? Let's take an example. You have the new, then your friend, then right? And then let's say it has some router. And this is the server which has both dog and cat. But now you're going to send out a packet that says, give me dog. Right. So assume that these routers know where dog exists. Just assume for now. And it sends the packet along like this direction. And dog. So dog.jpg comes back in the same direction. And while it is coming back in the same direction, all of these routers, right, they will also keep a copy of dog. This router also keeps a copy of dog. Router also keeps a copy of dog. Okay. Now, of course, and after this, you're going to get back the response dog over here, and you're happy. Now, imagine your friend wants to also get the image of a dog. So what will he say? This is in the context of information-centric networking. Right? So what will your friend say? Give me a picture of a dog. So you're sending out a packet with the destination as a dog. This is the name of it. Right? What happens? You're sending it, and the moment it reaches this router, the router has a copy of dog. Right? And you will get back the response right from dog. Right? So this is how information-centric networking is expected to work. And this is a conceptual aspect till date. But there are challenges in this information-centric networking. What are these challenges? You see, you have the original picture of a dog here, and then you have the duplicated pictures over here. What if the source changes? Will it be propagated across all of these? Correct? So consistency. Challenge. Second, overlapping names. Let's say I have another server and I'm going to name something as dog.jpg. But imagine this dog.jpg contains a cat's picture. So what happens there? Right. This is a very naive example. And also, thirdly, security aspects as well. So I can introduce any resource on the internet that will overlap with all the other resources, and it could go wrong. Right. So these are all some of the challenges associated with internet networking, and one way to address this is the naming scheme. It's the naming scheme, and other different types of naming schemes. One is flat, one is hierarchical, the other one is attribute based. So essentially, what we're trying to do with naming schemes is to assign something unique to the name, right? So what does flat do? If you have a cat.jpg, it runs this through a hash function, right? And then you get some x, y, z, uh, 1, 2, 3, things like this. So you add this cat and x, y, z 923.jpg. Basically, you say this plus this, then you get the unique file name, right? So you can make your resource look unique, and you can distribute that resource name to everybody, right? And then next is hierarchical. So hierarchical is something like this. So you have your folder structure in Windows, right? You go into multiple folders. For example, you go into pictures, then you go into animal, then you go into domestic animals, then you go into dog, right? And then so and dog.jpg, let's say. This forms a unique hierarchical structure. And if someone wants to add another one, so it will be cat. All this will remain the same. Um, so this is hierarchical naming convention, and attribute based would mean that you have a picture. What's its resolution? Okay. So every attribute about that particular resource, right? Resolution of the image, which is nothing but some pixel value, right? And you add all of these attributes, right? And then you also have what is the unique about a picture file and what able to. But some, let's say one more attribute as well. Let's say size of the file, right? So you take these attributes and then you add it to cat.jpg plus size plus resolution. So this forms a unique way to identify the image. So this is basically what information centric networking is. Okay, so now let's take a look at the questions quickly. I'll just give you the answers for all of the name data networking parts, and I don't think we have time for data plane programs. Just and just here's what are the questions. Okay, related to exam types and questions, right? Okay, okay, yeah, sure. Although I'm not an expert when it comes to exam questions, just give you some general pointers. Mm. Right. So anything to study apart from real lectures and assignments? I, I think I should answer your questions after I have a discussion with uh, the organizers. So probably, yeah, I think that will be a better case because this is my first time teaching in NPTEL. So probably next year I'll know what kind of questions they'll ask. So I think you're going to face the exam in the next 10, 20 days. So I think the general strategy should be like this: to be completely thorough with what you have studied, the questions and the assignments in the based on the video lectures that you've seen, and anything above and beyond that, you should be in a position. You would be in a position to handle anything above and beyond that also. So to keep the video lectures and the assignments at the core of your preparation. Right? That should be sufficient. And if there are any other information, so I'll probably communicate it to you all through the forum. So that should be good. Or probably you can ask this question in the forum as well. Right? So that would also get you the right answers. So I'm actually, to be honest, I'm not sure what kind of questions they're going to ask. But Amru, be prepared with what you have in the lectures and the assignment questions. I think the list of all assignment questions are available, I think, to you every week. We discuss it, right? And also you have one more great, good amount of student teaching on Fridays. So probably in some of the classes where you feel that one of us has not explained a particular question well, then you can go to the other video and you can see how that has been explained there. Probably you will get a better idea of that. Right? So in fact, I'll quickly give you the solutions. Probably don't have time to discuss these. By the way, you guys are free to leave. I'm already above time. So I'm just going to give you the answers for these questions, and they're quite straightforward as well. You can see the video and you can understand the answers. But yeah, as the fundamental objective of live classes, we are to describe the question answers for this questions, right? We have to give you the answers to these questions. So I'll do that job right now. Um, okay. Okay, so question zero or other question one, I can say. Uh, how many different packets are used in Indian architecture to retrieve a name chunk from a content provider? Very similar to ICM, right? Um, so what are the two? The answer is two. What are the two? They are interest and data packets. Right? And second, how does NDN handle data caching? Um, is also very similar to ICN as I was explained. So it caches using the intermediate modes. That's the answer. So intermediate nodes can cache data that they receive from content producers. So, and they serve that data to the consumers that request the same content. That's straightforward, very straightforward. Which of the following statements are correct about named data networking and IP architecture? NBN network, like IP packet delivery, employs best effort data retrieval. Uh, yes, it's true because it is there is no assurance. You're going to try your level best, right? So that's basically how the whole internet works right now. It's best effort. And it is wrong. And this is IP has a stateful data plane, not necessarily. So IP into the security primitive directly at the network layer. There's nothing like that. There's nothing like that in the basic IP address stack. So one interest packet can fetch multiple data packets in NDN. Nope, that's not possible. And the routing plane of IP is some, whereas the routing plane of NDN is small. Not really, right? You all route based on either the name or based on either the IP address. So here the following columns are addressed by Indian name and NBA Indian name-based routing. So the problems are addressed. So address space exhaustion, NAT reversal, and address management. Right? So these are the three problems that are addressed. So why are these problems? Because IP addresses are limited. Correct? How many IP addresses are there? IPv4, let's say 2 to the power 32. So this is something to 4 billion. Now we have more than 4 billion devices. So if each of these devices get their own IP addresses, let's say in a hypothetical world, you can't serve. So in a lot of ways, NDN is basically name based, right? So it is practically infinite. So in a way, address space exhaustion, address management, yes, is addressed by this name based routing. And NAT reversal. So what is NAT? I explained it in one of the previous videos. So network address translation. Network address translation. This is NAT. Basically, you have your private network. Let's say it's your campus, whichever college your campus network. This is the internet. Your IP address is 10.0.1.1 here. But if you someone from out, if you're sending a packet from here to let's say 179.7.2.3, this packet, once it reaches your border router and it comes out of your border router, it will have a source IP address of the border router. Let's say the border router IP address is 29, 30, 40, or 1. Your source IP address will be equal to the border of the source IP address. So that's why if you, for example, you go to your computer and then you type in IP config. If you have Windows IP config on your, I think I'll show you, right? I'll show this to you. Possibly. And okay, right, I'll show it. We'll finish this and I'll show this to you. Right? I'll explain what the network translation is. I'll live demo. So okay, next is which are the following is the key difference between the CS and PIT tables. So the answer is C. The CS is used to store data, while the PIT is used to store the interest of the unresponsive data. Okay? And question number 6, rather was 5. So the following are the reasons why NDN may be more efficient than IP in terms of network resource usage. Right? So the answer is A and B. Um, so data packets can be cached uh, at intermediate nodes, and because of that, it is more efficient than IP. The reason you don't have to go till the source of the content producer. You can get it from somewhere in between. It's like a universal distributed cache, and interest or data packets can be forwarded to multiple producers slash consumers. Right. So this is also possible, right? Can be forwarded to multiple producers or even to consumers. So basically the shortest path forwarding strategy is the default in NDN. It is not always used, and routers can use other forwarding strategies based on resource availability. So NDN may pose challenges to data privacy and availability, uh, and also corresponding security and caching policies should be implemented to mitigate these risks. Right. So this is basically the justification for why the other two options are not correct. Right. Okay. And then question number 6 or other 7. Yeah. Moving on. So the following statements are correct about naming in NDN. So it uses hierarchical and names are generated by the application. So these are correct, and of course they have the ability, and Indian does support. Right? So these are wrong. And next question is in standard Indian architecture, how many data structures does each router typically maintain in order to process Indian packets? There is 3. What are those? CS, PIT, and FIB forward information. So the next question is the following statements are incorrect about the security in NDN. So we're looking at incorrect, right? So NDN uses end-to-end encryption to protect content in transit. No, it does not. And encryption is mandatory for the data packets transmitted over the network. No, nobody even spoke about encryption in all of this. We're worried about routing, right? These are not the correct answer. But of course, the system cannot be attacked. No system can be attacked using information obtained from the. Oh, sorry. The system cannot be attacked, right? Yeah. And the content producer will cryptographically scan the data packet. Right? So that is basically making the data unique. Right? And what is the role of NDM trust model? Just to ensure data authenticity and integrity. So who produced that piece of data, and whether the produced data is integral or is it compromised by some external factors. Right? So these are all the correct answers. Now I'll just briefly show you NAT and then we can close off.
So you're not audible again.
Okay. Now I should be audible. Now I should be audible. Now I should be audible. Now I should be audible.
Yes, yes.
Okay. So basically, what I was saying was, you check your IP address on your phone system using the command ipconfig. Right. So where is your IP address? It's over 192.168.234.1. If you're having a Linux system, you type in this word ifconfig. You'll get the same details. But then you checked your IP address on the browser. So you're saying that your IP address is 103.232.241.199. So who's correct? Is this correct or is this correct? So the answer is both of them are correct. So this is your private IP address. This is your public IP address. Now, how does a private IP address get translated into a public IP address? That is through the process of network address translation. So this is just a short practical demonstration for you to understand that addresses inside a particular network are called private. But once a packet goes from inside that network to the outside world, it will take up the IP address of the border route. Right? And why is this? And you might also see that the same IP addresses could be repeated for somebody else sitting in someone in a distant home. Let's say you're talking to your parents who are staying far away from you, and they are connected through a laptop. And both of you are using different modem. You are in a different city, they're in a different city. Your IP address could also be 10.0.1.1, and their IP address could also be 10.0.1.1. So these are addresses that are present inside a private network. The moment you move outside, you need a these really uniquely identifying IP addresses. These are public IP addresses. These are not repeated, but these can be repeated. These are private. Right? So private IP addresses are repeated, public are not repeated, they are unique. And private IP addresses are meant for reuse. And network address translation is the way in which you can translate between private IP and public IP. Right? Yeah. So I can understand that this week I did not concentrate much on NDN, but probably because there is two videos and you can easily answer these questions if you watch those videos. The major objective that I had today was to give you is to kind of rehash what you've learned throughout the ACN and how it is different from the basic computer networks course. Um, uh, and yeah, so you must have learned some new concepts all through this 10, 11, 12 weeks. And all the best for your exams. And possibly, when you study for the exam, try and understand what you're reading and get a sense of what you're reading about, right? For example, STM. You can always read STM as okay, it's software defined networking, and control plane separate, data plane separate. So try asking the question why was it separated, and probably you'll understand the subjects in a more better way and help you further if you want to pursue a career in network or a career in yeah, as a network engineer or even a career in network security, right? So yeah, I think that's pretty much it. If you have any questions, you can ask me, or if not, then we can leave. Okay? And you can reach out to me if you want any questions. If you have any questions regarding any of the classes in between, or to Ranjita as well. She teaches on Fridays. Yes, yeah, that's pretty much it. Yeah, I probably should have given my contact also on the. Okay, so you can reach out to me on this mail. Um, I mean, conceptually, if you have any doubts, just send me a mail. Or definitely try and respond back to your questions, right? And yeah, and I think towards the end you can. So this is me. I think I should um, give you this also. You can reach out to me through. In case you don't get that, you can reach out to me from this website. It has the contact details. And if you're interested in, let's say, networks or networking, you can reach out to my research group as well. So if you want to pursue a career in this, and if you're interested in research per se, that's it. Feel free to reach out to me, and we'll see if you fit in any of the projects we're working on. Yeah, but that's pretty much actually. That's the website. Okay. Oh, thank you, Nico, because right. Okay, I think I mean if you ask me, I didn't do a great job of I do a great job of in the questions, I believe. I mean, at least in terms of problem solving, right? I try to explain the answers. Um, I basically try to explain the concepts in a very fundamental way. That was my objective. Possibly, I think I'm happy you learned how to solve MCQ, but maybe next time I'll give more emphasis on trying to teach people how to solve MCQs. For that, I myself also have to become a bit competent in it. But yeah, anyway, sure. Okay then. Good night.